I have to give you your Fanta and your Butterfingers.
It's true.
What kind of Fanta? Orange?
What are you taking away?
I'll get her one.
I mean, I think it's one of the
Yeah, I feel like it went pretty quick.
What?
All right, so what I'd like you to do is take out your calculator, please.
I never thought so.
On your desk. Yeah, little souvenir. This function that I have typed up here is not on your page, but I wrote it so that I didn't have to write it multiple times. I'd like you to, in your calculator, plug in the function, the quantity x plus 1, make sure you put parentheses with that, and then divided by x. Draw yourself a little graph. Try and make it pretty accurate. Like, you don't have to see specific points if it's crossing the x or the y-axis, but like, try and look to see what's going on with it. Why is it leveling off at a specific location? And then our goal is to see what happens as x approaches infinity, because this is limits at infinity. As x goes to infinity, as x goes to negative infinity. And as I said, like, minimal algebra. Not really algebra. And more properties. What's the graph look like?
It's like two curves
Mhm.
approaching 0 from the negative side, and then going down, and then approaching 0 from the right. And going left. If
So,
that makes sense.
going up? Is that what you mean? Going up. Like this?
Yeah. And then
Something like that. Okay, so I agree almost with what Kate said, except as it's like leveling off horizontally, it's a little closer. Virginia? It's gonna, get close to y equals 1. So it's gonna level off, not at 0, but just a little bit above that. So it's gonna level off at 1. Does anybody know why from the equation it kind of flattens off at the 1? Virginia?
Because there's a plus 1 on top of it.
And that is what everybody has said today, which I understand why you're saying that, because there's a plus 1 there, and usually that plus 1 shifts the graph. But it's not because of the plus 1. Chelsea?
It's because of the horizontal asymptote from x.
So she said it's because of the horizontal asymptote. What's happening with the exponents of the x, Chelsea?
They're the same.
Right, so when the exponents have the same degree, or when the x's have the same power, the number in front, the coefficient, is how you get that asymptote. We're going to review that again today. So not because of the plus 1, which is deceiving, because that plus 1 is there, but that plus 1 actually shifts the graph left. That's what the plus 1 does. So it's because of the power of both x's on top and bottom are the same. The coefficient in front of them is a 1. So that was one of the 3 properties of horizontal asymptotes that we talked about. So if power is the same, then the asymptote exists at the coefficient.
If it shifts it left, why does it look like it goes to 0?
What does it look like it goes to 0?
Yeah.
I don't know what you mean goes to 0.
You said the plus 1 shifts it left. And why is it like leaning here?
Oh, because that's the denominator is undefined at 0. It's shifting the it doesn't necessarily shift the asymptote. It's shifting like the intercept. But that's the denominator is undefined at 0. That's why there's that. The 0 there. Other questions? So looking above with the little notation here, this is actually how you're going to see a limit. So we're going to see the limit as x approaches 0, as x approaches infinity. So as x is going to positive infinity, the limit or the y value or the function, because they all mean the same thing, is going to approach 1. So wherever that asymptote is, would be where our limit would be approaching. Oh, there it goes. Maybe it's okay. So x is going to infinity means my graph is going out further and further and further to the right. But since it's leveling off horizontally, my graph is approaching, the y value is approaching, the limit is 1. Whatever terms you want to use, they all mean the same thing. Going the opposite direction, negative infinity means I'm now going to the left. And again, the graph is leveling off horizontally underneath that value of 1. So it's going to get closer and closer and closer to the value. So the limit as x approaches negative infinity, the y value would be 1 or the limit is 1 because of the asymptote. So asymptote kind of creates the limit of the graph. So infinity, as x approaches infinity, doesn't mean that it doesn't exist. So instead, we're now looking at the outer part of the graph and seeing what's going on with it. Instead of looking at like x approaches 0, x approaches 3, and negative 1. So just because it's an infinity doesn't mean there's not a limit because we're going to a number that we don't really know is there. So underneath, there's a little bit of limit notation here. Pretty much the key thing with this notation is just for you to understand that if x approaches infinity, there is a limit. It's not that it does not exist. So just because it goes to infinity doesn't exist. That isn't the case. So right here, the limit of f of x as x goes to negative infinity could be one number. The limit of f of x as x goes to positive infinity could be a different number, or they could be the same, like the one above. So L1 and L2 are limits that exist dependent upon where the asymptotes are of the graph. So we're going to look at a second one graphically, and then we're going to see if we can do them without relying on the calculator, without relying on the graph, but just kind of thinking of some properties that we remember about asymptotes. So if you want to look at that second equation, you can place that in your calculator again and give yourself a little graph. I think it's the 1 over x equation. You might not need to put it in your calculator. Some of you might remember what that looks like. Did that vent like shut off completely over there?
Yeah.
I didn't hear it anymore, so. Not sure if I should be worried or they all shut off. I mean, the electric shut off earlier, so maybe the vents.
Do you know why that happened?
Mhm.
It was like not just the school. The
It
mall was
happened
up
in Miss
too.
Stubbs
Oh, really?
like 7 times.
I did not know that.
Yeah.
That's not.
I'm thinking someone hit a telephone.
That could be
The
some-
second
something,
it- the
probably some
second
kind
it
of
turned-
important
Yeah.
generator.
The second the power went off, this girl Emily said, we're all gonna die.
I was hoping for it. What?
Brandon, you know what the graph looks like?
No, I don't.
Oh. Anybody know what the graph looks like? Chelsea?
It's the same thing but before, but the horizontal asymptote is 0.
Yeah, so this one has a horizontal asymptote at 0 because there is not an x on the top, just a 1. And we have the x on the bottom. So this one goes down to 0, follows the y-axis and the x-axis. So same graph as above, except now the asymptote, the horizontal asymptote is at x equals 0, or y equals 0. So this limit, as x approaches infinity, my y value, which is the limit, is 0. It's getting closer and closer and closer to 0. It doesn't touch it, but it continues to skim along next to it. So underneath it says, notice as the values of x get larger, the fraction value gets smaller. Therefore, it approaches 0. So this is kind of getting you to think of what's really happening with the value of the fraction as a whole. So if you plug a 10 in, I have 1 10. If I plug 100 in, I have 1 100. This number is getting smaller. If I plug in a 10,000, it's getting smaller.
But it's not 0.
That is not 0. So whatever number you plug in here creates a really small number, but it never becomes 0 because the 1 on the top. There's no way for it to become 0. But it's going to get really, really, really close to it. So with fractions, when there's just a numerical value on the top, a variable on the bottom, the fraction can get really, 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 really small. When the value on the denominator is huge, your number gets small, but never 0. So we're going to try and apply that to the problem underneath, which I keep forgetting I erased, and I have not had time to place it back in here, obviously, since it's still not here. So this says the limit as x approaches infinity of 4 minus 3 over x squared. And it asks you to evaluate it. Not sure what the directions actually say. Nope, it doesn't give any directions. So how would you evaluate it? There's like 2 different things that you could do. The easy way and the more algebraically involved way. Let's go with the easy way. Okay, well that would be the really easy way. I was not obviously thinking calculator. Virginia?
You just plug in values and see what.
So we could plug in values and see what it looks like. What else could you do, Eris?
Same denominator.
You could get a common denominator. That would be the algebra. And Kate just gave like a horrible face back there. She clearly doesn't like that idea. What else could you do with the operation? Thinking about the operation, like how could you separate it? Instead of getting a common denominator and pulling them together. So we are allowed to look at this as two separate individual functions by just taking the limit as x approaches infinity of 4, and then also the limit as x approaches infinity of 3 over x squared. So we're still going to kind of do what Virginia said, but we're going to look at them as two pieces.
That looks too much like logs.
Logs. So two functions are really here. We could combine them together to make one by getting a common denominator, or you can separate them and look at them as two separate parts. So the first one, if this is a 4, really that means it's y equals 4. That's your function sitting here. What kind of graph would that create? So Brandon's back there drawing a horizontal line. Your horizontal line is always at 4, so therefore your limit is also always at 4. So this has a limit of 4. Because the limit is the y value. Well, the y value is always at 4. It's never changing. It's always 4. Now, thinking about the last two problems, what would the limit be of 3 over x squared? Virginia?
0,
Why?
because you can get infinite numbers for x squared, so it just gets infinitely small fractions.
Exactly. So whatever number you're plugging in for x, you're going to get a smaller and smaller number. Even quicker than the one above because you're squaring it. So if you plug in a 10, now I have 100 because I have to square that number. So the limit of this one is just 0. Anytime you're going to have a number divided by x, it's always going to be a limit of 0. So my limit would be 4. You'd get that same limit if we combined and got a common denominator, as Eris said. But you can look at them separately and just think about what is that number telling you? What does that graph really mean? What does the graph look like? So horizontal line always has the same limit. Every horizontal line has the limit of where that y value is located. The fraction has the limit of 0. So subtracting 4 minus 0 is just 4. Questions? So on the back we have a couple of little shortcuts, which you guys like shortcuts. So we don't have to rely on the calculator. You have minimal to think about algebraically. These shortcut rules, it says apply to limits at infinity, but also were the same rules that we talked about with horizontal asymptotes. And there are 3 of them. 3 different conditions based off of the horizontal asymptotes that you have in the graph. So the first one gives you an example with the limit as x goes to infinity of 2x plus 1 over x squared plus 3. Does anybody remember what happens with that type of problem? And what you're really comparing when you're trying to think about horizontal asymptotes? Virginia?
That would have a horizontal asymptote of coefficients over each other. Either 2 over 1.
What's happening with the powers of that one?
Oh, it's a smaller power than a larger power.
Yeah, so she said the smaller power, which is the degree of the numerator, is less than the degree of the denominator. So we're looking at the powers or the degree. So the smaller power is on the top compared to the bottom. What does that mean about the asymptote?
Isn't it a 0
It
because
is-
it would make it smaller every time
Right.
you plug the averages?
Exactly, so that gives us a value of 0. So if the larger power is on the bottom, no matter what power you plug in there, what number you plug in, your fraction just continues to get smaller and smaller and smaller. So that's when the horizontal asymptote is at 0. So if the power on the top is smaller than the power on the bottom, having that larger power, forces the fraction to go to 0. So we have a horizontal asymptote at y equals 0. That means we have a limit also at 0. So we've got that horizontal asymptote like the 2 problems we looked at graphically. The second one, looking at these powers, in this case, the degree of the numerator is equal to the degree of the denominator. So what does that mean about this problem? Aisha?
It's gonna be 4.
Excellent. So the limit is going to be 4/3 because there's a horizontal asymptote at 4/3. So when the degrees are the same, it's the coefficient in front, the 4/3, whatever the coefficient happens to be. And then the last case, the last option here, Brandon, what's happening with these powers?
The power on top is greater than the power on the bottom.
Yeah. What do you think that means, Brandon?
Don't
Do you
we have to
remember?
solve for the numerator?
Kate, do you remember?
It doesn't exist.
What doesn't exist?
The limit or the asymptote.
Right, the limit doesn't exist or the horizontal asymptote doesn't exist. Does anybody remember what kind of asymptote there was?
Wasn't it like a I don't remember, I'm not gonna call it everything, but it was like a slanted line.
Yeah, and that's what it was called, a slant asymptote. Nice job, Kate. So there would be a slant asymptote, not a horizontal one. So there are 3 easy problems, and a lot of your homework tonight, like 13 through 17, 21, 27, 31, I think 33 changes, are like these 3 problems. Examples, find the limit. That's it. So look at the powers. You have 3 options. How does that problem compare to one of those 3 shortcuts for finding the limit? So we have negative 2x cubed plus 3 over 3x squared plus 1. So Co, what do you think about the limit of A? What's happening with those powers, Co?
There's no limit.
Yeah, there is no limit. It doesn't exist. The power on the top is bigger than the power on the bottom. So letter B, Eris, what do you think about that one?
0.
And that's because the power on the top is smaller than the one on the bottom. So that fraction is going to continually get smaller and smaller and smaller and closer to 0. And then Libby, letter C is,
Negative 2 divided by 2.
yeah, negative 2/3. Looking at those coefficients. Any questions? So the other little part of this section kind of goes back and gives you a quick little glimpse of a sequence, which I am actually talking right now with my kids about sequences. Mr. Rebar, I think, is wrapping up sequences because he does sequences before we do probability and statistics. Anybody remember what a sequence is? Huh? Oh, that was the sigma notation, yes. So that weird E thing was the sigma notation, the way we got a shortcut way of writing a sequence. Really, if this is a true sequence, it should have an n in it. Sequences use the variable n because n represents the position that your term is in. Is it first position? Is it 5th position? Which means where is it at in the sequence? So is it the 5th number of the sequence? Is it the 10th number of the sequence? Generally, x usually is represented in equation. N represents a sequence. With sequences, they're infinite. They continue on and on and on. And last year, we actually graphed sequences and found limits of them by plotting points. So a sequence is a set of points. It's not a connected curve or line, because when you have a sequence, the first position is totally separate from the second, and there aren't any like half positions in between. So this one here, we have the limit as, I'm changing it to an n just so that it's like sequence form, approaches infinity of 1 over 2n. Underneath it, it says this sequence is said to converge to 0. So yes, sequence have limits. If it does have a limit, we usually use the word converge, because they're kind of curving towards a number, getting closer and closer to a number, converging towards a number. Why would this go to 0? Chelsea?
Because you could plug any number in for n, but it would never actually.
Exactly. So whatever number you plug in for n, you're never going to get the value of 0, but it's going to get closer and closer to 0. The last little sentence underneath here says that the sequence does not converge, then it's said to diverge. So essentially, if it has a limit, it converges. If it has no limit, we say that it diverges. And that's because it's a sequence, so of course it gets a special name. So I'd like you to flip, we're going to do 2 more little problems. Just kind of thinking about a sequence. A sequence is just a list of numbers that have a pattern. So in this case, these numbers go from 1 to negative 1, 1 to negative 1. I could continue on, 1 to negative 1. It says this one diverges. What's happening with those numbers? What word did we use earlier in the week? Oscillates. Oscillates means that they bounce back and forth between the two numbers. Like that heartbeat monitor kind of is bouncing back and forth between the values. So it diverges because it's not going to one number, it's going to two different numbers. So this one does not have a limit since the sequence is bouncing back and forth. Again, it just gets a special name. They say it diverges. The last problem that I want us to look at today wants you to kind of think about how to calculate some numbers in a sequence. So I want you to find the first 5 terms of this sequence, and then it says find the limit. So we have the limit as n approaches infinity, which truly denotes, like recognizes we have a sequence. And then we have 2n plus 1 divided by n plus 4. How do you think you'd find terms of a sequence? Brandon?
Can we plug in -2 to 2?
We could plug in -2 to 2, but generally where do you think a sequence would start?
0.
Not even 0, but usually it actually starts with 1, because my first term, the first number in the sequence is considered term 1. The second number in the sequence is considered term 2. So we would start with a 1. Sequences use this A notation. A sub n is usually how it's written. So A sub n equals whatever that notation or whatever the equation would be. And then you just plug in the 1. And then that calculates the first term. So I have a 3 on the top and a 5 on the bottom. That would be my first term of the sequence. And then you plug a 2 in, and so on. So Brandon, the second one would give you,
5, 6.
the next one, Brandon, would be,
1.
yeah. That's 7 over 7, so you get 1. And then Brandon,
It would be 12. It would be 12 over 8, which would be 3.
you're so close. 2 times 4
Oh,
is 9 over 8. And then the last one is 11, 2, 5, 10, 11 ninths. Yeah, 11 ninths. So we have our sequence. Going back to the original equation, it says find the limit. Sometimes the sequence might not give you the whole limit, but if you use the properties of asymptotes, what limit would this have? Brandon? 2. So eventually, if we calculated more numbers in the sequence, you'd see that they're going to get closer and closer to 2.